Welcome back, everyone. And today is going to be a fun day. Today, we're going to explore a new topic called voxels. I've been saying that we're going to explore this at some point, and today's the day we're finally going to explore it. For anyone who doesn't know what a voxel is, voxels are basically three-dimensional grids. That's technically all there really are fundamentally. Um, like this image, for example, is a three-dimensional grid, and that's really how you really can imagine what how voxels are. A very popular example of voxels is Minecraft. Minecraft, here's another image, is practically just a big voxel world. It's just a bunch of cubes. It's just a giant, massive grid, and everything's built around the idea of three-dimensional grids. And you can do a lot of things with it. You can create whole worlds, kind of like, like Minecraft. You can do character animations, kind of like this voxel critter creator. You can make characters and you can animate them, and, fun stuff. You can do a lot. There's voxel art. There's voxel games. Sky's the limit what you can do with voxels, in all honesty. Sometimes the things are built in voxels, but they're not very cube-like. There's I think No Man's Sky is a universal voxel type of thing, if I remember correctly. So it's a whole world type of situation. so yeah, and the idea of voxels, is pretty simple. It's just grids and points and various I don't know what else I can really say. Here's a really good example of some voxel pixel art. So in this part of the series that we're going to start dealing with voxels, we're going to work toward a goal. We're going to have a milestone. In our series, sometimes we have milestones, like the model viewer in the very beginning of the series was a milestone. King's Kite's Planet was another one. That's when we're spending a lot of time doing procedurally generated content. We created a whole mini planet procedurally generated, just nothing but code and math. With voxels, a lot of examples are really just building large terrains and planets with them, and that's all fun and dandy. But everyone does that. So I want to try something different when it comes to voxels, and I want to build something like this: a Portals 2 map editor. If you ever got to see the Portals 2 map editor tool, it's practically all voxel based. Just by seeing how it works and interacts, everything's cubed, everything's pretty cool, and the way you interact with it's pretty neat. I like the idea that you can select, and then you can just extrude and move things around. So we're going to try to kind of create this sort of thing in the end. So this will be our milestone to actually build our voxel chunks in our voxel editor to basically build a tool like this on the web page. And it will also function as a mini game, because we're also going to have Bendy. And Bendy's in there because it's part of Valve and part of Portal's series. And we're going to have maybe we can build like an actual chamber and then have our Bendy character kind of walk around it. So that'll be like the end milestone at the end of armatures and voxels, is where we can merge the two together and make a mini game out of it. So, but again, like I said, this is going to be the end goal, is to build this sort of editor in WebGL and from scratch, like everything else, and try to get, we're not going to build all the little bits and pieces, but at least be able to build a room and reshape it. Kind of like how they do. You'll be able to select things, move it in and out. You can do some really crazy things. You can make the size a little bit bigger. Just by adding more chunks to it, you can make the room bigger and bigger. And maybe we'll try something. Maybe we'll include water into the mix. So maybe we can have some water sections in our voxels, things like that. So yeah, the sky's the limit, but yeah, I really want that's kind of where I'm hoping to get toward when we're dealing with voxels. We're going to build that instead of terrains, and I might do a tangent from here to there, where I might deal with terrains. There's certain things I have to when you're dealing with terrains, especially like unlimited terrains. We might need to do some Foxstrom calling. things like that. So there's a lot of little things here and there that we'll need to do to be able to handle terrains in Voxel. I know some people might say, hey, do marching cubes. That's another thing we might explore as well. So like I said, there might be quite a bit of tangents here and there when we're dealing with voxels. But the end goal is to create that portal room editor, that chamber editor. So this way we can actually make a mini game in this series. I've been doing this series for almost a year now, and I want to really start making this, make a game instead of just making systems that build towards something. That hopefully builds towards some kind of system that we can make games out of. Hopefully we're getting to the point where we got enough built in understanding of the underlying system of things related to game development, graphic programming, that we can start doing some fun stuff. So let's start off with maybe some theory. I'm going to do something completely different. I've only done this once before, so I was thinking, let's just do some whiteboard. I'm going to break this video down to two parts, and this part is going to be mostly about theory, some mathematics, and putting together just the base code to kind of get like a 2D voxel thing working. And then the second video will then focus more on 3D. So, so voxels are a cube, right? So that's what I pretty much started the series. It's a 3-dimensional cube, and I'm going to do a really bad job of making a 3-dimensional cube. So we have a cube. So that's essentially is a single voxel item or an entity. But when you create voxels, we have to build them in chunks. So entire worlds are built as groups of voxels. Like, worlds aren't built as one giant voxel grid. It's actually been made up of many voxel grids, which are called chunks. So one thing you do with you can do a lot of things with voxels. You can size them any way you want to, but normally for specific reasons, voxels are kind of just subdivided. So, and in this instance, this is one voxel. I'm going to subdivide it, and this ends up creating 8 cubes. So we're basically turning this 8 cubes into one giant cube into 8 individual cubes. So now we kind of start having the idea of a voxel grid. So it's a 3-dimensional grid, and you can kind of say this grid is a 2 by 2 by 2. X, Z, Y. And you might say, why X, Z, Y? Well, we're going to build everything on a flat plane. You can build this in any way you want to. You can build it, so let's say we have an axes. So this is X, and we're looking from above. So we're from the above. So this is kind of our ground, because our ground in WebGL is X and Z. So we're going to build it from the ground up. But if you wanted to, you can do it more like this: X and Y. Build everything forward and then build depth. It's your personal preference on how you want to build it. In our situation, I'm going to build it from the ground and then build up as height. Okay, so that's pretty much it. Now, the next thing we need to cover is data. How do we handle voxel data? And there's actually many different ways you can handle voxel data. One very popular method is called octrees. The idea is, especially since we're subdividing, so you basically have one cube. Then you subdivide it, just like what we did. I don't want to. 1, 2, 3, 5, 6, 7, 8. I know I'm doing a horrible job. So the idea is then you take that one giant cube and you subdivide it by 2, by a factor of 2, I guess. So 1 becomes 8, just like how I drew up here. And then that creates 8 cubes within a chunk. What you can do is then subdivide these even further. And when you subdivide every single cube within this giant cube by subdividing it, you end up creating a total of 32 cubes within a single chunk. So that's kind of an octree. An octree are basically parent-child relationships. So that's one way you can formulate the data. You can formulate the data as parent-child relationships. So you kind of start with the parent node, which is one cube, and then you kind of just break it down level by level. And depending on how you want to manage the data, you can actually have everything at the ground level and then kind of build up. Octrees are very useful when we're doing raycasting. Octrees are used for a lot of various other things as well. So it's just not voxels. So that's one way to kind of manage the data. If you want to, we can just do it straight up with octrees. But octrees are limited in the fashion that you kind of have to do everything in the power of 2. So everything kind of gets subdivided. So that's kind of a more complicated way of going about it. Another way that's kind of popular is multi-dimensional arrays. If you're doing with other languages, you can sometimes access array like this. So it's kind of like X, Y, Z, one single bracket. You can just automatically assign multi-dimensional arrays. I think JavaScript can support multi-dimensional arrays, but I'm not sure if it can handle 3 dimensions. I think it can handle just 2. I'm not exactly sure. Why not? Let's just check it out, because I probably should check it out beforehand. But let's just see. JavaScript multi-dimensional arrays. Does it have like straight up support for it, or? No, it does not have, by the looks of it, does not have straight up multi-dimensional support. So it's so it doesn't really have it, or maybe there's, I don't know, maybe there's better documentation in a newer version. But let's just assume it doesn't have it, because not all languages do. So like I think like Java and C or C#, you can do multi-dimensional arrays like this. So you can just predefine what the dimensions are. In JavaScript, you kind of have to basically create an array. So you have, let's say you have like 2 elements, and then in element 0, you make it another array within it. And then element 1, you make another array out of it. And then inside those arrays, 1 becomes another array, 2, whatever the element is, so on and so forth. So you kind of have to build arrays on top of arrays on top of arrays. So it's not kind of like a straightforward thing like how it might be in more high-level languages. So if you're accessing arrays like with JavaScript, you kind of just have to kind of do it like this. So you kind of do like X, and then you have another bracket which kind of references the next one, and then another one. So that's how you can access multi-dimensional arrays like this. Some of the pros and cons. The pros is it's very easy to access the data. All the data is easily organized. You can just grab X, Y, Z. You can build your 3 dimensions very quickly and easy this way. The negatives is a lot of lookup. You have to do a lot of data lookup. I don't know if that's a big issue with JavaScript. Maybe it is. Maybe it's not. When you're dealing with C++, sometimes too many lookups can slow you down a little bit, but especially if you're doing a lot. It's only when you're doing like tons and tons of things. So you kind of might want to limit how many lookups you're doing, like memory lookups. So things like that. And when you're stuck with a multi-dimensional array like this, you can't just loop straight through. You kind of have to do multi-loops, or you kind of have to do a single loop, but then that kind of keeps count of 3, that tracks the 3 counters, or 3 intervals, or whatever. Let's call them counters. The 3 counters, so you can change them. So you actually have to write a lot of code, or just do 4 or 3 for loops to actually manage it. What else? So that's that's that. If you want to do it that way, a lot of people do it that way. Let's see what else. Very bare bones, super simple. Not necessarily simple, super simple, but since this is a 2 by 2 by 2, we have 8 pieces. Let's say if we're just dealing with voxels of bits are 8 pieces, or like divided, just subdivided once. That's 8, right? So a very simple solution is you have a single byte equals about 8 bits. You can actually probably store this as 2 bytes if you really wanted to, if you want to do more. But let's just say we're just dealing with this one as an example. You have 8 bits. So if you wanted to, you can say, well, I'm going to store this cube as a single byte, and I'm going to store it this way. I'm going to say 0, 1, 1, 1, 1, 1. And now I can say what 0 means is I don't draw that cube, and 1 means I do draw that cube. So if we're going to, let's say if we're building from the top to the bottom, this one would say this cube should not be drawn at all. And the rest of the cubes are built in that chunk. So you can basically store things at the binary level if all you care about is on and off states at a per level. And you can store more, like a single integer equals 8 bytes. So, you have 8 times 4, 8, 16, 16, yeah, 16, 32. So you can get like 32 bits of information in an integer. The only problem is with an integer, it's signed, so the final bit is negative or positive. But if you can do an uint, like an unsigned int, you get a perfect control over 32 bits of information. So 32 is a good size for voxels. You can do higher than 32 divisions. But like I said, by just using a single uint, which doesn't exist in JavaScript, mind you, you might be able to do unsigned integers, but there's no really types in JavaScript. But if you're going to do this in like another language, and you want to store things as binary data, it's not 4 bytes. I'm sorry, it's uint store data in 4 bytes, but it's 32. It's 8 bits for 4 bytes equals 32 bits in general. Sorry, that's 4 bytes equals uint. So yeah, you can store 32 bits of information that you can then use a controller. So you can actually store all this information in a very, very tight amount of space. So that's another solution if if you only care about on and off states. What we're going to do ourselves, simply because of that's how I want to roll, is I want to do a single dimensional array. So let's say in the case of 2 by 2, I'm going to say 0, 1, 0, yeah, whatever, fine, 0. I'm just going to draw one cube, and that's going to be, we're going to draw just the bottom half, right? So the bottom half has 4, and then the top half. I'll do that. So we're going to store everything as a flat array. So this is 0, 1, 2, 3, 4, 5, 6, 7, and we can incorporate that into this information. So we're still, now these are actually integers. I'm not saving these as binary bits. This is just an array with integers. So we are wasting 8 times 8 worth of information. But one of the reasons why I kind of want to do a flat array, is because we can kind of just run through a flat array very quickly and very easy. And we can do some tricks with flat arrays. And we can still access everything else in a 3-dimensional array. So we can create a function called get x, y, and z. So we're going to make a function to call that, and we can translate that information, and we can get the index value in that array. So let's say we have our grid. We say we have here's x, here's z. So let's see. That's 1. And that's 2. That's 1. And that's 2. So let's say I want to. That's 0, 0. So let's say I want to access. Let's assume each point, like right here, these are cubes. So this, let's say we're dealing with just one row of cubes. So that each point is really just a cube. We're just thinking about it as in data. Like these are the 4 points. So I want to access, let's say, this one, which will create, let's see, x equals 1 and z equals 1, right? And y equals 0, because we're not going into the third dimension. We're going to stick with the 2 dimensions, so we're sticking with y. And don't forget, y goes up, so we're building from the bottom up. So I want x1, x2, or z2, x1, z1. So the first thing we need to define is how big our grid is. So we know our grid is x, y is 2 by 2 by 2. So we can say x length equals 2. We can say z length equals 2. And we can also say y length equals 2. So we have those values. So we have to know the size of our grid in general. So no matter which direction we're going, we're always going to know x. X is always going to be the right spot. So that's x. So x is going to be 1. All right? So x is always going to be the value. Now, if I want, so no matter which direction I'm at, like I said, no matter what row I'm at, x, the column, is always going to be the same. So x here, or x here, x here, x here. It's always going to be the value of 1. But what I need to determine is how far in the z direction it's going. And to go to that far to the z direction, so you have to go z times x length. So z is 1. I need to go 1, 2, 3, 4. I need to go 4 steps. I need to go 1, 2, 3, 4. There's 4 steps, right? That's 4 steps. Like if I was going to do like a continuous, like in an array, I got to do a continuous movement. So 0, 1, 2, 3, 4. So that's kind of where I need to be at that point in time. So for me to go, so if I know the row length is 2, so that's one whole row, and I got to go a whole another row from that starting point. So the idea is x plus z times z, not z, x. Let me undo that. Times x length. So if that's 1 plus 1 times 2, so that's 2, that equals 3. And if you're going to do an index, that's index 0, 1, 2, 3. Yeah, 0, 1, 2, 3. Because I'm not starting at 0, so 0, 1, 2, 3. Okay, there you go. So even I mark these down, because index starts at 0, so it's really here. So it's 0, 1, 2, 3, and that's 3. That's our index 3. So 0, 1, 2, 3. Here's the spot we're looking for. It's the 4th element, but it's 3 on the index. And the same thing applies when we go to 3 dimensions. So if we want to go to 3 dimensions, we say y times x length times z length. Because just like how if we want to go from, let's say x is here, but then I need to move it up a row, I have to go z times the length of a row. If I'm moving the grid from a 2D to 3D, I got to go that whole grid's distance away. So if I want to move this into the 3rd dimension, I got to take the whole grid worth forward, or in the flat array. So if I know my flat dimension, my 2D grid is really that times that. It's usually x times y, but since we're dealing with WebGL, it's going to be x times z. That gives us our grid length. So that's our grid length times y. How many grids, how many levels, like how many floors in the house are we going up? So if that's 1 floor, that's 2 floors, that's 3 floors. So so basically taking like the size of the floor times how many floors we're trying to get to. So this is really the equation equals index. So our get function, we can pass in our x, y, z coordinates, plug it into this kind of equation, and then we can get the index value of our flat array. And that's how we can then access it. Now, we only need to do that when we need to access data in x, y, z kind of way. But when we're building the actual voxel, we can actually just loop straight across. You know, we just loop all the way through the array and not have to deal with this all the time. Yeah, so that's really the gist of it. Now, the last thing that we can probably now have to talk about is how are voxels built? Voxels are built face by face, just like a grid. So let's see. Let me pick a light color. So let's say we're building this flat world. So this is kind of like our data. We're going to check. Let's say we have this index. We have the data for this index, and it's 1. That means we want to draw this cube. So when we want to draw this cube, we're going to have to go loop around and check its neighbors. So we could check this neighbor right here, right? And if this neighbor has, actually, you know what? Let's use this one example. This one's the example. So we want to draw something. So we want to draw this cube. So the first thing is we're going to check, let's say, north. It's north direction. Because you got to remember, that's z, and that's x. So we can treat everything as direction. So this can be north. This can be east. This can be south, and this can be west. So when we're dealing with this kind of flat grid, we can then check these neighbors, and on top of that, we can go, you know, up and down. You know, we can get that third dimension as well, which doesn't kind of fit in, but we need to check the up and down as well. So let's say I want to draw this cube, I'm going to check to see if this side has a cube that's going to be drawn. And when I check the north, I see it basically I'm going to return a null because there is no cube. This is the edge. So I'm going to build this face. So that face is the quad. So we're going to build a quad just like that with the triangles, like we've done like since the first 3D lesson. And then you kind of just loop around. So we're going to check this side. Does this neighbor get to be drawn? It's like, well, there's nothing there, so yes, I'm going to draw that one. Then you check this neighbor. It's like this neighbor is going to be drawn. Like let's say for some reason that is going to be drawn. So we don't draw it. So I'm just going to simulate that this is going to be an invisible quad. And we're going to check this face. Well, that one's going to be drawn too. So this one's going to be drawn. This one's going to be drawn. So I'm going to simulate that as well. So this face and that face over there is not going to be drawn. They're invisible. Those quads will never exist. But the north and the east facing is going to be drawn. So you're going to have two quads. Then we're going to check the top and bottom. And we can say, well, there's nothing on top. It's null. So that one then becomes drawn as well. And you get the nice little quad. It's kind of messy. I'm sorry about that. But that's how you end up building a voxel. And you do the same thing at the bottom. And depending on what kind of voxel system you're doing, you don't need to draw the bottom. Like if you're doing a voxel terrain, the bottom doesn't need to be drawn at all. So, like I said, it depends on what you're building. If we're going to do the level editor, we need to draw the bottom. So, and that's how you end up building it. You just check the neighboring data to see what's being drawn, what's not. Like if it's not going to be drawn, we're going to draw that face. If it's not going to be drawn, wait, let's say if it's not going to be drawn, you draw the face. If it is going to be drawn, you don't draw that side face. So that's essentially the idea that you're going to do, and it's like it's X, Y, Z, whatever. So my throat is really in bad shape today. So that is really the gist of voxels. So now let's look at some actual code and get it working. So we're going to have to start with a very simple, basic template. We're not doing anything special. Now, the first thing I did is really just use our VO standard stuff and start building the faces, because I want to be able to draw the faces. So right now I'm showing you voxel chunk faces. So we don't need to look at voxel chunk yet. Excuse me. So, but this is the part of voxel chunk that I kind of built first before I built any of the functionality for it. First, I did some constants. So remember I showed you the north, south, west. I built it in. I set it up in an ordered array. So this way we kind of loop around, and I put down as last because, like I said, sometimes you don't need to render it. So if we don't need to render it, maybe they might have a switch that says no down or include down or something like that. So if we're going to run this as an array, we just have to loop between 0 and 4 when we don't want to render down. But if we want to, we just go 0 to 5, and then we render it. And I built the faces in the same order as the order that we're going to do the looping to actually build it and look. So if we're looking north, we're going to build back. If we're going to build east, we're going to build right. If we're going to check south, we're going to build front, so forth and so forth. And I predefined all the values as 4 components because I'm using these as tests for colors, and I might use something else later in the future. But I did leave a comment that says I might not need it in the future. So, so these are really the 4 voxel coordinates, or not voxel, the 4 vertex coordinates to build a quad. And these are the indices to actually turn these 4 points into 2 triangles. And I built everything in the exact same way for each specific direction, so this way the index value is the same, and the UV values are also the same, because voxels need to be textured. So this way we can kind of, the normals and the vertex information is unique, and index and UV can be shared amongst all 6 faces. So I kind of built this in a nice optimized way, so this way we can just duplicate this data over and over again really quickly. So if I go back here, the base code really just does this. So we're just drawing this one face. And if you see the colors R, G, B, and then black, so that's going to be 0, that's 1, that's 2, and that's 3. And no matter which face we decide to draw, let's see, this is going to be the back face. I keep going back to that. Refresh. There's the back face. So if we spin this around, it's still the same color, RGB black. So like I said, I went ahead and built all the faces and made sure that by using that color component, I made sure the points all are exactly where they're supposed to be. Like that's where I want 0 to be, and that's where I want 3 to be, and then it goes in a counterclockwise so I can draw my triangles. And I want this to be, because this is where UV starts at 0, 0. So it'll be 0, 0, this will be 1, 0, this will be 1, 1, and this will be 0, 1. So like I said, everything is built to be identical no matter which direction. And everything is built at origin. So, oh my God. Let's see. Like forward. Which one's forward? Forward is 2. So 2 right now is right on origin, but ideally when I'm going to build a voxel, it has to be over here. And what I'm going to do is use the normals and say, well, this normal, I'm going to have it offset to here. So I'm just going to move it one offset off to here by using the normal values. And same thing with left. So left is built here, and I need to shift it over to the right. Now the reason why is because when we're depending on how the voxels are going to be built, I might want to use this face, but for the back, or I might want to use this face for the front, because when it comes to dealing with the portal editor, the back face is really going to use the front face quad. So it's built that I can use it for both. It can kind of be interchangeable over time. So that's why I kind of built it that way. And like I said, that's really just the bare bones. Now we want to start building our voxel. So like I said, every voxel thing is built in chunks. So here's our voxel chunks. So we can define how big we want our voxel. And right now I have it defaulted at 2 by 1 by 2, which is going to create like a flat 2D voxel. That's what we're going to try for right now. Just in the next video we'll do 3D voxels, but today we'll do like a 2D voxel. And we're going to set scale because we kind of want to set the size of our overall voxel. So I want to really 0.2. And this is our overall length. So the values that we're passing it is the total length, like the size of our grid. And then I'm going to cache the maximum value, which the maximum value is really just the length minus 1. Because if we're dealing with indexes and things like that, the length is really the length. It's kind of like it's a number system between 1 and n. And this number system, like since we're dealing with like index starting with 0, because we're dealing with arrays, we always kind of have to be off by 1. So it's always, so instead of being 1 to n, this one's from 0 to n minus 1. So that's the kind of like the direction we're going. And then I also cache the total size of our 2D grid, because we can reuse this in the mathematics later. Like I said, that equation to get the index is going to be y times this, times x length times z length. So since we're going to be doing that a lot, like, you know, if you're reading like 100 voxels, there's no point in doing this multiplication over and over again. So it's a good idea just to cache it, and so this way you can reuse it and save it. And our overall size of our grid is just like, you know, if you're going to do a grid, it's just x times z. But since it's three-dimensional, we just take the three sizes and multiply them together, and that's how many overall subdivision cubes that we're going to generate for our chunk. Like, remember in that drawing I did where I took a cube and I subdivided, you know, if it's 2 by 2 by 2, so 2 times 2 is 4, 2 times 2 is 8. So that ends up creating 8 cubes. So each cell in our three-dimensional grid is it's going to be 8 cells to generate that that voxel chunk. Now this just fills in the entire chunk with the values of 1, so this way we kind of denote it that we want to draw. So that's really just the constructor of our voxel chunk. And this is just test data. Let me set this back to all 1. So this way you can kind of control what we're going to draw. But like I said, this is just garbage. This is going to be deleted down the line. This is for testing. Now we have the get function. Like I said, we have that get function that gets our data, and it uses our math equation right here. X plus z times x length plus y times xz length. This is the original way I wrote it, and then when I sat down to optimize it, I made it a lot smooth. Like, I don't need a modulus. I don't know why I used the modulus, but I used it. But now I don't really need it. And everything else kind of works together. And you can do it in one big equation. And over here I have cells, and I call the function. And if I really want to be very efficient, especially if I'm using this function a lot to get the information per voxel, it's better off me just putting the equation in here, because the idea is why is a good idea for this. Now, the way it is this way, that means let's say if I'm calling 100 voxels, I want to get information for 100 voxels. So after all this crap is done, I'm gonna have to do a function call that converts the coordinate system into an index value. So that means I have to call this function, which then does all the math, returns the value, and puts it in here. So that means, let's say if I do 100 calls, I have to do an additional 100 function calls, which, you know, I have to stop the processing of this function. This one has to set up the memory and everything, all that jazz, just to get that function set up and ready to go to be used. So ideally for optimization, it's, you know, it's duplicating work, but sometimes you have to duplicate for if you want to maximize your optimization, you know. So this way, I just by putting the equation in here, I remove one function call in this whole total process, and it's just a math equation. Sometimes they say the most optimized code is the least readable, you know. So keep that in mind. Down the line, I'm actually going to optimize it even further and move this equation into this function. But right now, I just leave it like this, so you guys get the idea of what these things are. And then this get function has this extra little bit where I actually can get the neighboring data. So right now the default is -1, so this way it does not get a neighbor. So instead of writing two functions like get voxel and get voxel neighbor, I decided to combine the two. So say I have one function, so I can just say XYZ. I know where I want, but I want to grab one of these neighbors. So I want to grab the north-south because I want to compare this specific voxel that I'm currently processing, and I want to know what its neighbors are, so I know if I'm going to draw a face or not. And then this part just checks to see if everything is within the bounds, and that's why I kind of have everything kind of cached, because we use this stuff a lot. So it's like I said, so a lot of things that I try to cache the values at the root level. So this way we can, you know, we can maximize certain function calls that can be done like hundreds of times as much as possible. So we try to do as little math as possible. So at this point, I'm kind of saving a lot of math operations and just converting it into memory lookups. And I know I'm saying these things that makes no sense to a JavaScript developer, but in the end of the day, this is going to be all written back again in C++. So that's why I kind of look at this as like, okay, this has to be optimized for C++ in the future. So I'll write it in JavaScript as if I were going to write this in a real application with real optimization. So that's why I might be saying, that's why I'm saying like functions and memory lookups and things like that. But it'll help JavaScript too. You know, what's good for the goose is good for the gander. So every little bit can help in JavaScript, because JavaScript is just built on top of C++ anyway, and at the end of the day. So anything you can do to help out, the better. So this, like I said, this checks the bounds and returns null if you're checking part of something that's outside the voxel boundary. So remember I said, like, okay, we're going to check north, but that north, there is no data. It's that we turn null, so that we know we're on the edge. So every time you get a null value, you know you're on the edge cube inside the voxel chunk. And that's all that it takes to create a simple voxel chunk of information. You know, we just have a way to access the data, a way to access its neighboring data, and how to tell if it's an edge. You know, like I said, we get a null, and just how to translate our XYZ coordinate system into an index for all our voxel information. Now, one thing I want to note is that right now we're going to save a value of 1 or 0 in RLSLs, but in the future we might end up converting numeric values into a struct or an object or something. So we might want to store multiple chunks of information per voxel. Like for the level editor, we might want to know what texture we're going to use for that voxel. You know, sometimes it's a dark texture, or sometimes it's a whiter texture. You know, depending if the wall can be have a portal on it or not. So in the future, even though all this will stay the same, the data we store in the cells can change. We might have to fix the renderer a little bit, but overall everything kind of stays the same. So using this flat array doesn't hurt us in the future. It actually we just change the value within that array, how we access it. So that is our voxel data, and like I said, it has all our drawing stuff. Some of this stuff I'm thinking maybe I should move it to really the voxel renderer, or maybe I make a new class just called voxel, and that will hold all the information. So this way, this array, this class object or this object doesn't have to hold it, because voxel chunk doesn't really need this information. So I might do more optimization down the line and really just break this apart maybe into 3 classes. So I could say just hold these constants away from voxel chunk. But for now, it works. So now we're going to the final part, where is how we render all this information. And it's kind of like just like any other renderer we have. So we pass in our voxel chunk, our material name. We're going to use triangles, and we're going to have calling turned on. I think it's on by default, but calling is turned on. And we save our chunks, and we build our mesh based on our voxel chunks. Like right now, we're just going to build voxel, a 2D voxel. So, and we're going to use a two for loops. And in the next video, I'm going to probably do this in a single loop, so you guys can see it a different way to approach this. So right now, we're going to do like what the easy way to do it. You know, just this loop between z and x. We're going to loop our rows, and then for every row, we're going to loop every column. So once we know our x and z, we're going to ask for the data. So we're going to do the lookup, and if it equals 1, that means we're going to draw this. This cube has to be drawn. It's not an invisible cube. So we take the vertex array. Now here we have an array, and we're going to store all our vertex information. At this point, we're building our mesh. We're building all our triangles and our quads. So I'm going to say how many vertices have we saved so far. So right now, in the first loop, we have 0 vertices. So 0 divided by 4 equals 0. So that's our index, and that's our starting index. So we're going to build a quad, right? So that means we're going to have 4 indices. So there's going to be 0, 1, 2, and 3. So once we build those vertices, like I said, we have the vertex 1 is index 0, vertex 2 is index 2, and so on and so forth. So we build our vertices, and the only thing we do with our vertices is that when we create the face, we translate it. So if we're on, let's say, the beginning of our quad, like x is 0 and z is 0, we're going to build we're going to put all the 4 points right next to origin. But if let's say if we're at x is 1 and y is 0, that means we're shifting over a little bit. So we kind of add in that extra 1. We're going to shift it 1 more time. So we're basically changing the value of these points. So let's say if I'm building the front face, all these x values get changed into 1 because we're shifting them over 1, because we're now, accessing x equals 0 and z equals x equals 1 and z equals 0. So we're kind of just moving forward, and you'll see how it works and how it works. So like I said, we're going from grid cell to grid cell, and we're going to build it in those positions. And our fourth component is just that color value, and we're going to use that index to build our indices. So our indices uses our index value, so which is right up here. Here's our indices. So like I said, remember I said if we're building the first quad, we have the starting index is 0. So we add these values to 0. If we're building the second quad, that means we already have 4 vertices in there. So 4 divided by 4 equals 1. So yeah, it was 4 equals, equals 1, right? So that's length. Well, it'd be 4 times 4 is 16. It'd be 14. It'd be 16 floats. So 16 floats divided by 4 creates 4. Means there's 4 vertices. So that's what's going on. This is vertices. So there's, like I said, there's 4 vertices, but the data is kind of all flat. And since we have to save this as for the buffer, we have to save everything flat. So we're saving so it's 4 floats that generates a single vertex, and by taking that length divided by 4, we get the index, or like basically what we get is the count, a vertex count. So this is really the vertex count, how you calculate the vertex count in our flat array for our vertices. So 16 divided by 4 equals 4. So that means we are on the 4th index. So if the first time through we said it was 0, so 0 plus 0 equals 0, 0 plus 1. So these indices are the perfect indices for the first quad that we draw. So the second quad we draw, we already have 4 vertices in there, so we're going to add another 4 vertices. So if we're going to add another 4 vertices, the index is going to be between 4 and 7. 4, 5, 6, 7. Where the first one was 0, 1, 2, 3. So with 4, so we say 4 times 0 equals 4. 4 times plus 1 equals 5. That's 6. That's 6, and that's 7. So this way, by using that starting index value, we can just add it to this template of indices, and we can end up building all the indices for all the vertices for to build all the triangles. So it's kind of a really kind of sweet way I kind of put it all together. We've done things like this in the past. I just haven't really spent a lot of time explaining it. But if you guys have seen me do this from time to time and you got sick and tired of it, I'm sorry. But if you're new to the series, this is really what's going on. I'm building all the indices for every vertex. And just by using a little bit of math and by doing kind of like a smart way of organizing the data, I can actually get away with building everything in a kind of very simple way. So once we have our vertices and our indices all built up, we can then just render them out as any other mesh data that we've done in the past. So if I get rid of this, and now we just start rendering our chunks. I don't need that. So we got to recreate our chunks. We create our renderer. We pass in our chunks, and we just pass it to the list, to our scene. And if we click refresh, there is our 2 by 2 by 1 grid. It's flat because we're only drawing one face at a time. We're not doing 3D in this video. In the next part 2, we're gonna deal with 3D. So these are the faces that we're building. They're 1 unit big. Everything's kind of built at origin. And remember saying when we're going through the loop, we're shifting. So that's what we were kind of doing. We're kind of just shifting everything in the X and the Z position. We're translating as we're building. So we kind of use the quad information as kind of like a template, as a starting point, and then we modify it so we can move it around into 3D space. And here's the beauty of voxels. So let's say, so this is voxel 0, that's voxel 1, that's voxel 2, and voxel 3. So I'm going to hide 0 and 3. So if I go to 0, I'm going to say don't draw it, and number 3, I'm going to say don't draw it. And we click refresh, we don't draw it. So like I said, it loops through that array, and if it equals 0, we don't draw it, and if it equals 1, we do draw it. We create the quad in that place. And the last thing we haven't implemented is scale. Since everything is built at like basically unit length, everything's between 0 and 1, it becomes super easy to scale things with those values. So if I want to, let's say, scale the size of our voxel, I just take our face or our vertices and scale the vertices. So I'm gonna take the vertice information and I'm gonna scale it by the X and Z. And same, you can do it Y as well, but we're not dealing with 3 dimensions right now. So if I scale just that, now I got our 4 voxels scaled to the size of our grid, because our grid is 0.2 units big. That's how I designed the grid. Now the problem is that our grid is now scaled to size that we want, but it's not positioned to scale. It's still using the unit length. For translations. But so we can actually translate it. Like I said, we're using whole numbers too, so which also becomes unit values. So we're doing everything by one. So we can actually just scale the actual translation as well. So if I scale X and Z, I can actually group everything together. So now our voxel, now we can control how far apart our voxels are and the size of our voxels. And ideally, you want the size and the distance apart to be equal. That's why I'm scaling the translations, and I'm scaling the actual size of our vertices. Ignore the seams. That's really just the grid drawing on top. Let's see. Let me see. I haven't tried this, but set position 0, 1, 0. If I move this, there you go. Now you can kind of see there's no seam at all. So it's a perfect voxel, and we kind of just moved it up. I just wanted to show you that those seams that we saw was just the grid being drawn on top of our voxels. So our voxels are drawn perfectly, like touching each other. And that really ends the basic necessity of how voxels are put together. You know, we got the voxel chunks. We talked about different ways to store the data. You know, we're like I said, we're doing like the flat array, and we're kind of going to translate that information or XYZ coordinate system into an index. And it's done very easily with very simple math, just 2 additions and 2 multiplications. And we kind of walk through some basic, how to traverse the data. One way of traversing, because like in the next video, I'm going to traverse it differently as a flat array. Because right now, like I'm treating it, I'm traversing it as a multi-dimensional array. Next time, I'll do it as a flat array. So this way, we only have one loop that deals with all the work. And like I said, this generates vertices, that creates triangles. We might create a second loop that makes an identical, or almost identical this, that creates the UV values. Or, I might not deal with that and maybe build a voxel shader where I can use this component as, I can use the fourth component to dynamically create the UV values. Because that's 0, that's 1, 2, 3, yeah. So yeah, I can probably do that if I want to save myself. Like if our voxel, trying to think, if our voxel data is there's too much. Like that's maybe a nice optimization is not to actually use UV values, not actually create a buffer full of UV values. Maybe it might be easier just to use the fourth component and then just use an index and just have our vertex shader hard-coded with these values. And that, I don't know if that might be better. Like, definitely less data. We have less data, but now we're pushing to the GPU with an if statement, which has to be done once per vertex, which might not be that big a deal. We won't know until we try, rendering like 1,000 voxels on screen, and then create 2 different versions of it and see which one has like a better frame rate. So like I said, I'm not sure how to go about it yet. We might do some optimizations down the line and play around with that. But this is really the bare bones to kind of get started with voxels. Next video will be like we'll complete it, which would do the 3-dimensional. But this is kind of a good starting point. Like I said, it shows you all the bare necessities to really just to get there, to get to that point. So I'm going to save and end the video here, and set myself up to do part 2 because I want to do this as 2 parts. So please like and subscribe, and I'll see you guys at the next video.